Hello and welcome to today's episode. This is Rawkode Live. I am Rawkode/David Mackay, and I am very pleased today to introduce a whole host of people. As we can see here, we have six, including myself, guests today. And I'm going to delegate the introductions because it's too many new names for me and I'm not very clever. So I'll introduce Paul Burt from OpenEBS and MayaData. Please take it away.
Yeah, howdy. Thanks for having us. We're deeply invested in open source, so we figured we'd bring the open source community with us. It's kind of the plan here. So I'm the director of community and marketing at MayaData. We build OpenEBS and Litmus Chaos are kind of our top tier open source projects that you may recognize. I think we're going to explore Mayastor, which is a new kind of fangled component of OpenEBS that does some really cool stuff with technology from Intel and Linux Foundation projects and other stuff. So we have Kiran Mova, who is one of the co-founders of MayaData along with us, and he's the architect of OpenEBS. We have Jeffrey, who is our CTO at MayaData and works deeply on the Mayastor project. And then Glenn Bullingham and Jan, I think, are product management and architects, software developers, correspondingly. So we've got a full house here today.
Yeah, we're setting a record for the most guests I've had on this stream at any one time. So it's awesome. Now, I believe we're going to start with a few slides just to talk about what OpenEBS is. So, Kieran, I believe you're going to share your screen.
Yes, thanks, Paul and David, for having us here today. Let me see if I can figure out, share the screen here. I haven't prepared slides specifically for this event, but I do have some slides that I want to share from the last presentation that we had at KubeCon. It'll be a trimmed down version of it before we get into the most interesting stuff on Mayastor. Just to set up a context on the origins of OpenEBS and how we came down to working on Mayastor. So this was a slightly, older survey now. It's from 2019. 2020 is going to be published at the upcoming North America KubeCon, but OpenEBS is one of the most evaluated storages in the open source for stateful workloads on Kubernetes, and we call the storage pattern that we have implemented as container attached storage. And while we are the leading open source platform or container attached storage example, there are like some commercial options available as well. Like Portworx, which was recently in the news, is the one that I was also featured in the survey. So the origins are pretty simple. Like I think we think that Conway's law is kind of getting realized right now at all industries. In some recent article that I read, there are no more only the data companies kind of survive now, and every company is a data company, whether it's Bloomberg or could be Benz, or every organization has become like a data organization as well. This is a story from CNCF end user report, which talks, which kind of represents the way teams are organized at Bloomberg and how Conway's law can get applied there with respect to disaggregated teams, small number of teams working on several thousands of microservices, and a much smaller team supporting or what you call a platform SRE team supporting them. And this is possible with Kubernetes and other CNCF technologies that enable these teams to automate their entire infrastructure as a service within their organizations. So though Kubernetes started off as an orchestrator for stateless workload, it's kind of soon transformed, or it's enabling data to be run in Kubernetes as well. And we also see this shift coming from the way databases are architected as the teams are transforming from specialized or layered teams to more functional teams. Even the types of databases that are getting deployed within these are different. It's not a single database that all the data goes to, but rather, depending on the service that you are providing, your databases are optimized for that. We tend to see now a wide variety of databases in an organization's stack. So a few other reasons, especially with respect to agility, that's driving the teams to go into microservices and disaggregated, is also this notion of data gravity. Once we end up using some existing technology or like a data layer, even though we kind of are becoming better with agility in terms of application development and the choice of databases, but the real data gets stored onto some platforms and you kind of get locked into that one. And this can actually slow down the growth. This is one of the reasons why we thought we should not get locked into any kind of storage when you're running your applications. And we try to see how we try to provide you this data like a vendor agnostic way of setting up your data infrastructure. Um, and the other thing is about the new hardware that's available and new technologies or like new techniques that are available to make optimal use of this new hardware. For example, this shows a 96 core machine with almost close to 1 terabyte RAM that's available on the node. And none of the existing technologies can fully optimize the power of such boxes, right? It's almost like, even the when you're talking about processing the IO, how do you go from working at like that are optimized for working at 4 core or like 8 core CPUs to 96 core CPUs, right? Uh, Things around the storage also have been changing. A lot of stacks around the storage infrastructures have been rewritten. In fact, like uh, by using the IO ring or lockless mode techniques. What we are trying to see is, okay, now we have NVMe protocol that can work at a much faster speed than the traditional protocols. Can we make use of the newer hardware and the transport protocols that are faster and enable you to process more IOs to deliver you high performance storage? Uh, and another interesting aspect was about the shift towards user space to provide you with a better software delivery experience, or while not compromising on the um, performance itself. User space tends to make us believe that, okay, we are going to lose out on some performance, but I think what we want to show via the Mayastor project, that, and Mayastor isn't the first one that we attempted. We tried to do this with a couple of other projects, and before coming up with putting all those learnings from the previous projects. Most of us on the call today come from ZFS background. That was focused on maintaining the data consistency, but at the expense of like performance. We tried to get those learnings to build Mayastor that's both uh, developed on open standards, providing you the performance and optimizing the infrastructure that you have. Um, so rewrite was inevitable, and we will try to walk through Mayastor, which is our latest engine, and see how some of these aspects that we developed really came to life with that. Um, just in terms of few more slides, or like, these are the early adopters, or like that we have for the OpenEBS project. It's actually, the list is quite big now with 25 or more public references, and we also have like many more customers and partners talking about OpenEBS as the or the container storage as a way to deploy your applications. And we actually support both local PVs, make it easy to run local PVs, as well as support replicated storage, right? The reason for doing that, the cloud native workloads tend to have the distribution logic built into them. Many a times when they're getting started, they just want a local storage which is operating at the speed of the disk. So for these, we make it easy to run, consume the storage that's available on the nodes and carve it out and provide it to the applications without adding like data services like snapshot capabilities, or like a few other things like optimized backups or incremental backups, that kind of stuff. But as we have noticed that as people start using this, they get really comfortable, but once they run the applications for a longer period, they tend to ask for other capabilities as well. Like snapshots, backup, restore, and encryption. Those things are what are getting built into our replicated stack via Mayastor, which operates at the speed that local PVs can provide you, along with providing the additional data service capabilities. With that, I will hand it back to David and Jeffrey in case they want to add something more to this. Um, and then we'll walk into the live demo session.
Yeah, I guess thanks, Kieran, for the quick introduction. I guess the only thing I want to add to it is that the idea with Mayastor is that we wanted to re-architect a storage stack in user space because it runs in containers, and so you need the implicit ability to be able to decouple yourself from the kernel, because all kernels are not the same throughout the cloud providers. And the focus there was to embrace the new technologies like NVMe over Fabric. And the only real way to squeeze out these performance numbers is to use these lockless models. And that's not because it's cool. It's actually very hard. It's very, very hard. Asynchronous programming is a nightmare, really, no matter what language you use, really. But the interesting thing that has happened recently, not that recently, but relatively recently, is that storage is now much faster than the CPUs, and that in history has never ever been the case. And so it requires some rethinking, and that's what Kieran alluded to with the hardware changes and IOU-ring, which is a new interface to the Linux kernel, for example, that has a different way of submitting work to the kernel, and that is because the hardware is much, much faster these days. But in order to make use of IOU-ring, for example, it's not like, oh, I install IOU-ring and off I go. It's like, no. You really have to rewrite your application, unfortunately, right? So all these things together, cloud native design, rewriting the software, languages with concurrency primitives built in with Go func instead of pthread create, these type of things. It's a very exciting time, I think, and gave us for us, it provided the justification to at the very least give this a shot. So Mayastor is it's still early, but we've put a significant amount of work in it already, and so that's roughly it. I hope that makes sense.
Yeah, I have some color. I feel like a fifth grader who did like a book report last week, and I get to present it now. Something that has helped this all make sense to me is thinking in terms of what Kieran was saying. Direct attached storage is kind of the easy thing you reach for, but it lacks features. And eventually, in certain projects, you may get to a point where you want network attached storage. You want features like encryption and all the fancy. Sorry, I've got an angry, hungry cat in the background. That's Miss Bits for you. So you're looking ultimately for getting started simply, but growing into something that's a little more professional or a little more featureful down the line. And OpenEBS has been designed such that we can support multiple storage solutions. So we have a ZFS-based solution, we have a Longhorn-based solution, and what we're exploring today is Mayastor, which is based on kind of like groundbreaking technology. So there are projects like DPDK and SPDK. Are you familiar with those, David? I'm cheating, actually. I asked you this before the call.
Yeah, I am definitely not familiar with them. Can you, let's expand the acronyms first. What do those mean?
All right, so good question. So DPDK stands for Data Plane Development Kit. And the emphasis here is on development kit. So it's not a turnkey solution that you just pull in and off you go. Everything is hunky dory, and is oriented towards networking. And the genesis there is that is based on the fact that as you get more bandwidth towards your computer system, like 100 gig, 400 gig, or what have you, you typically have an interrupt-driven approach. So a packet comes in, the interrupt happens, the CPU stops, processes the interrupt, and then goes on its merry way. But as the rate of packets increases, what you see is that the dominant behavior of the CPU, or the operating system rather, is getting interrupted all the time, right? So it doesn't make any forward progress because it's constantly getting interrupted. So one way to get around that is and what you see is that you get interrupts that are white hot, so it constantly gets interrupted. And one way to get around that is to batch things. So you get an interrupt, it's like, okay, I'm not doing anything, not doing anything, not doing anything, and then boom, you handle multiple requests in one interrupt effectively. The downside of that is that your bandwidth goes up, your latency increases, right? So that's not ideal. So the idea of DPDK and projects that are built on top of it, for example, a VPP, vector packet processing from Cisco, was that, well, instead of having the kernel do all that hard work, why not isolate a CPU, 1, 2, or 3, or maybe 4, who knows how much you need, because these days we have cores to spare, right? I mean, the new Threadripper is like 64 cores, and it's a consumer product. It's like an insane amount. So instead of having the kernel do that, what if you do that in user space and isolate 1 or 2, 3 cores to do just the networking? And the benefit of that is the CPU doesn't do anything else than that. And so the caches, the level 1, 2, 3 caches of that CPU remain hot, if you will. And combine that with some additional technologies like huge pages and whatnot, you can actually see that it not only in certain situations outperforms the kernel, but turns out to be far more efficient because the kernel can now, worry about processes and things like that instead of just constantly doing the interrupt. So that's DPDK. On top of that, Intel also has SPDK, which is DPDK plus some storage-specific protocols like nvme and iSCSI, VirtIO as well. And but as mentioned, they are development kits, not turnkey solutions. So what we've done is we took those development kits, to so to speak, and we are using those in Mayastor to benefit from the work that they already have done, because it's a significant amount of work, and it is micro optimization tools. Like I've never seen that much optimizations before, where they pat things on cache lines, and it's like insane, really. And Intel has very specific software called vTune to do that. So I can't really do that, but suffice to say, it's highly optimized for a very, very specific task, and that's what these development kits stand for, if that makes sense.
Yeah, I mean, I understood at least some of the words.
Well, there you go.
But the short version for someone like me who doesn't have the deep kind of expertise of the rest of the panel here is you end up paying a tax when you're using the Linux kernel. It's been in development since 1991. So it's kind of got this tried and true figured out model that requires locking and doing all these kind of slow processes, where you'll pay like a 30% tax just by having the Linux kernel manage things for you. There's probably even deeper taxes that you pay having things sort of filter through the pachinko machine that is the kernel. And what these technologies are doing is they're connecting your program in user space, short-circuiting the kernel and going directly to the hardware, connecting you to the hardware. And it's DPDK as a solution supported by the Linux Foundation. SPDK, as Jeffrey mentioned, is supported by Intel. So there are big names investing in all these technologies and a lot of effort going into making these things really shine. And what we're seeing is they really do shine. If you've got a need for speed, these do some really cool stuff for you.
Yeah, there are other examples. For example, SkylaDB, which is a re-implementation to a certain extent of Cassandra, where they leverage that same framework to do some of the things that they're doing, like network I/O and things like that. And I also would like to emphasize that it's not a deficiency of the kernel for it not being able to keep up, if you will, but it's more like it needs to do so many things. It's like, give it a break, right? And that's basically what it boils down to. So it's not to say that the kernel is bad, not at all. In fact, it's just like, I mean, there's this thing called physics, and you can't beat that. And there is this notion of serialization that needs to happen in certain cases, and therefore it turns out to be somewhat more efficient to do it that way. if low latency and high performance is your primary objective. And when you're dealing with these low latency devices or high bandwidth devices, however you want to call it, then that indeed is what you need. So yeah.
Okay, cool. That's all really, really useful. I'm going to try my best now to take all of that information that we just covered in the first kind of 15 minutes and just surmise that as best as I can. And then I promise we'll go straight on to the actual hands-on portion of this. And I've already realized, which is really good, as you were talking there, that I've made my first mistake in the preparation. So that's going to be interesting. But we'll call it a knowledge transfer to the audience. And I forgot to enable huge pages, but we can do that live, right?
Yeah, sure. Yeah, okay. We do that all the time.
Yeah. Okay. So, in summary, and Paul, you're going to keep me right here, right? So,
yeah, for sure.
Stateful services on Kubernetes is hard because we have ephemeral compute and containers that has to move around. So we need the CSI specification, and OpenEBS is an implementation of CSI, which is the ability to provide storage to workloads on our Kubernetes cluster. Now, there seems to be multiple storage engines with OpenEBS. Now, there's a C-Store, which is the one which is tried and tested, and then Mayastor, which is the one which is currently in development, but has some pretty wicked performance gains based on the development kits that we were talking about just there, which I believe are written in Rust, which just adds an extra cool factor, or have I made that up?
Yeah. Oh no, you're right. Yeah, it's cool stacked on cool. We've got all the latest tech kind of packed in.
SPDK. We basically took the most cool keywords and sorted them and just collect them together. And yeah, no, but indeed, it's written in Rust and for various reasons. But one of which is based on the experience I've had with other storage systems, and 99% of the time the issue was a null pointer dereference or using something that's not there anymore. And Rust is supposed to help you catch these things earlier. Yeah.
Well, yeah. So the ownership semantics, if it compiles, it won't crash. Those are all really good benefits, I would imagine, for a storage layer.
Yeah.
Okay, so we've got our CSI implementation. We've got our multiple backend stores. I mean, the question in my head right now is, we're using Mayastor today, and we're going to show that off. Is that in a position where people should begin to adopt it in production, or is this a very much wait and see kind of thing?
So good question. And the thing is, there are certain factors that come into play. So we talked about nvme, and we also mentioned nvme over fabric. If not, then it's basically nvme over a network, whatever that network is. Could be RDMA, fiber, or TCP/IP. And one of the issues that is still there is that nvme over TCP was only ratified last November, so it is relatively young. IOU ring, which is something we use, same thing, is relatively young. So we are on the border of it's out there, but nobody's really using it. Right, so it needs to, as Kieran always says, it needs to cook. Right, we need to cook it, and it requires more cooking. But we are working on it with a team on a daily basis and trying to make it more robust every day. But it still requires some love and attention, let's say. But we're getting there rather fast, I would say.
Yeah, it's ready for your proof of concept. Let's put it that way.
Yeah.
Right. Well, I mean, I'm going to put it in production anyway, so I'll let you know how I get on. Okay, so let's finish the summary here. The multiple backend stores can run in two different variations, one of them being local PV mode and one being replicated PV mode. Does that apply to all of the backend stores or just Mayastor?
So I think per kind of what Jeffrey was tuning in on where doesn't work over NVMe over TCP/IP is relatively young. I think currently local PV is the only supported mode for Mayastor. Is that right?
Well, so it becomes a little bit complicated, I suppose, to express without my hands to begin with. But so what we do is, so let's say you have a Kubernetes node and that has local storage, right? The first thing that we do is that we don't have to, and that's where the complexity comes, but let's assume we always do for the sake of argument. We take that local storage, whatever it is, slow or fast, doesn't matter. That we are designed to be fast doesn't mean that we can't operate in slow mode. We'll do that just fine. We take that local storage and we can create what we call logical volumes on that storage device, such that you can create multiple PVCs in Kubernetes speak on that device, right? So we wire that up, so to speak. And the way that we connect to that local storage, so let's say it's a local NVMe device, there are several ways that we can connect to that. One is directly through the PCIe subsystem and user space I/O. We'll forget about that for now. Or URing, as we talked about, I/O URing, or AIO, which is the asynchronous interface in Linux that has been there since I don't know how long. Once we've done that, that's what we call a pool. From that pool, we can create replicas, as we say, and the replicas can be, or ideally are, scheduled across different nodes. Now, you don't have to do a replica, but if you want to, you should be able to. That's the idea. And per developer, per workload, you can determine if that is required. So let's say we create a mirror, 2 replicas. These 2 volumes are created through our control plane, which talks and understands CSI and creates CRDs in the control plane and whatnot while doing so. And these replicas are exported over NVMe TCP, but in user space, right? So we don't use the kernel for that. Then we create another NVMe controller that connects to those 2 replicas, and that NVMe controller is where the workload is, which means that the node that wants to write to the PVC connects to this, what we call nexus. It writes to the nexus, and the nexus then writes to the replicas wherever they may be. And that whole data path is in NVMe over Fabric. And so there is some nuances there in terms of, okay, the stability because of the newness and whatnot. But in principle, that's what we usually do. However, we can also directly remotely connect to existing iSCSI and or external NVMe over Fabric targets. But when I start to explain that, I lose people typically, so I'll leave it at that. Yeah.
No, that's
it sounds like generally yes. Yeah, both are generally supported, but it's like a Facebook status. It's complicated in the case of Mayastor.
It's complicated. Yeah, I like that one. Yeah. And so for all intents and purposes, you could say it's a proxy, right? Proxy. I/O comes in, 2 I/Os go out. Very simple. And then obviously the rebuild, and there's some of that, but in principle, that's what it is.
all right. Okay, so final part of the summary then. Hopefully I've not missed anything. What is recommended, or I guess encouraged, would be if you're running a cloud-native data store that handles its own replication, to use local PV mode and avoid that 9x storage costs. But if you're running more traditional databases that don't have replication by default, then it may be better to use that replicated volume semantics. And then the other thing that was mentioned, but I don't think we went into a lot of detail, is that OpenEBS provides a lot more than that as well. Snapshotting, backups, and other goodies too. I love I'll share my screen and what it says on the website, because there's some bold claims here. So Kubernetes storage simplified, which I just love, right? These are hard problems, right? And I'm really glad that you and your team here are working on the hard bits so that I can just have the nice, easy to consume API. So that's great. So simplifying storage is great. And then I love this one-line install, so to get started. So I think that now, unless there's anything you want to cover that I missed in the summary there, we'll just start kicking the tires on this. How does that sound?
Let's have at it. Let's break some stuff.
David, just to kind of clarify, so if we are going to use the existing bits like local PV host path device, this is the command that we proceed with. But if you want to try out the Mayastor, there's a different link that we should check out.
Oh yeah, we don't have to run this Helm command. I just love the fact that it's right there direct on the page. Like, I just love the ability for people to get started with a one-liner command. I think as developers, generally we don't want to read the docs. We just want to install it and then start poking at it. And that's good. All right, so let's cover where we are. I try, as always with this stream, is not to prepare too much in advance. So all I've done thus far is prepare a modest-sized Kubernetes cluster. So we've got 6 nodes running on Equinix Metal, each with their own. I used basically a heterogeneous cluster. We've got some large nodes, some smaller nodes, and some very big nodes. Some have lots of RAM, some have lots of disk, and I figured we could just talk about the trade-offs that we're making as we talk about that applied to OpenEBS as we go. And because we are going to need to configure huge pages, I have already kind of just split my screen into 6 so that we can get that out of the way first. I've never done this before, but I'm pretty sure I can replicate my input to all of these. I'll work that out in a second. But can we talk about first huge pages? Why do we need that for OpenEBS?
Good question. So the operating system divides memory up in so-called pages, and those pages are typically 4K. And the operating system needs to know where those pages are loaded, who's owning them, and whatnot. And it keeps a small table called, I just used the short term of TLB. I think it's transition look aside buffer or something like that. But suffice to say, it keeps a cache of which pages are loaded where. The more memory you have, the more of those pages you have. The more of those pages you have, the more likely you are to have a TLB miss. If you have a TLB miss, it is a rather expensive operation. I mean, it's nanoseconds, but if you have a lot of misses, then they amount to something. So the idea is well, why don't we use huger pages, like 2 meg? There's your answer. So you get less TLB misses, and that means that the CPU has to can focus more on the actual work than finding the right pages to load effectively. So that's and it really adds up. That's one reason. Second reason is if you want to do DMA transfer into a PCI address from user space, that memory location where you write from, and it's typically done with the scatter-gather list, as they say, is like write this collection of addresses into the PCI registers. At the moment you say that, you cannot have it. You can't have that memory gets replaced because it's virtual memory, right? So it can be swapped out and yada yada. And if you do DMA, it's like you can't have that. You can't all of a sudden move this piece of memory somewhere else, because by the time that we actually DMA it, what are we DMAing? So an undocumented feature is that the huge pages are what they so-called pinned into memory. So they are put in a location and they stay there. They don't move. And so those 2 reasons are why we use huge pages. Databases use them too, right? To reduce these cache misses and whatnot.
Okay, that makes sense. So how do I enable huge pages on the Linux kernel?
So you don't really have to enable them as much, rather than you need to tell the kernel how many you want. And there is a variable in sys mm or sys/kernel mm. I always use tab completion, so I forget. Where you can basically echo in the value of huge pages that you want, and you have 2 choices. You have the 2 meg pages or the 1 gig, and we always used 2 meg. And so you specify the amount of 2 meg huge pages. So if you want to have 1 gig of huge page memory, you specify 512. So from a usability standpoint, it's not ideal, right? But gets the job done.
So I can just echo 512 to /sys/
yeah. So let me open my browser.
maybe.
I always forget it because I use a declarative operating system next to a declarative.
I use NixOS, right?
Yes. How do you know that?
I run NixOS too. Not this
Really?
is my Mac for work, yeah. But
really?
Yeah.
Oh, interesting. So it is. Let me grab that thing here.
We can actually spin up Nexus on Equinix Metal. If I had known I had an Nexus expert on the stream as well, I would maybe have been as bold to try it. But
Expert is a big word, but considering all the other alternatives, this was the least worrisome, I would say. Let me see. Well, it's actually in the quick start. Maybe that's easier.
I've just pasted that one, Jeffrey, into your private chat, if that helps in any regard.
Oh, yeah.
Sweet,
so,
thank you. Okay, so let me just... I know people watching the stream are not really going to be able to tell because of the replication here, but we're echoing 512 to sys kernel huge pages, blah, 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 blah.
Yes, exactly.
We will stick that into the show notes in case anyone is curious.
Yeah, and if you then type cat proc / meminfo, I think it is, it should say, there you go, huge page total, 512, huge pages free, 512. Now, one unfortunate thing is that when the node runs Kubernetes, the kubelet needs to know about these huge pages. And unfortunately, for one reason that is unknown to me, however, is that you need to actually restart the kubelet. The kubelet is not updating those values. So we have to restart the kubelet. And then, if you have a bad day, then it's already game over.
All right. We have restarted the kubelet. Let's see if I can still run get nodes on my cluster. All right, I think we're good. So we've enabled huge pages and all 6 of our worker nodes at least. I won't bother with the control plane.
Yeah, right. Yeah. So, and then, oh, sorry, you just go right ahead. I'll just answer as you go.
Well, I mean, normally I try to follow the documentation, but I know that we're playing with Mayastor today, and we're maybe not going to be following what is recommended in the documentations, or is that an incorrect assumption?
Yeah, so we have a documentation for Mayastor as well. If we just go to the alpha features right there, and Mayastor, we should get there. It should point to our multiple redirection. I'll fix that. Yeah, that get good.
Sweet, awesome. So let's see what we need to do here. Now there are some prerequisites. I guess maybe we should kind of.
Oh yeah, well there's one interesting thing actually. There's the we use certain CPU instructions, and we kind of arbitrarily decided that if your CPU is older than 10 years, it's like, buy a new one, or not run Mayastor. So there's some of that, and it turns out though that the CPUs in the cloud are older than you think. But in your cluster, I don't think that's a problem. Yeah.
You don't think? I mean, that's not the most confident answer I've heard there, but we'll see.
Yeah. Well, the CPUs are not 10 years old there, right? So.
No. We've got pretty recent hardware, so it should be all right.
Yeah, exactly.
All right, so we've got modern CPUs, 4 gig of RAM, like that's not going to be an issue, and we've got huge pages which we've just enabled. So let's see, preparing the cluster. It's a bit difficult to read. I'll zoom out a little bit. Okay, so we did verify huge pages. We've said, oh, see, this was all documented. I should have just come here first.
We aim to please, David. Something about the manual.
I know. I think that I'm going down some sort of crazy off-beaten path here, and it's like, no, you're just following the docs. Okay. All right, so we have to label the nodes that we want to run Mayastor. Okay. Which means, I need my node names again. I hate it when I paste stuff and then I can't actually see where I am. Who'd have thought the hardest bit would be the copy and paste? All right, let's try again. Okay, so I'll just do the first 2 for now. Is that enough for us to get started, or should I run through them all?
Two would be fine. It will limit the number of replicas you can have to 2, but it would be fine.
I'm almost there now.
3 if you want to push the boat out.
This is captivating TV right here, so I might as well finish. All right, so last one. Okay, got my labels. Now we're going to the quick start. So this is just going to apply remote YAML. So this is just creating the namespace first.
That's right.
And this is just for the control plane of OpenEBS.
It's data and control plane.
Data and
all,
control plane.
All of the containers are created in a Mayastor namespace.
And then RBAC, everybody's favorite, and the CRDs.
I call it the cloud native pseudo, actually. But
so this is interesting. So Mayastor is using NATs under the hood. What's going on here?
yeah, so as we started to develop this thing, we realized that you may or may not want to have Mayastor running on all the nodes, right? So we needed a way to separate out the CSI nodes from the nodes that was actually running Mayastor, and we needed a way to register ourselves against the control plane. And after some trial and error with various approaches and concepts, we said, well, let's just use a message bus because that's where these things are really good at in terms of creating patterns and things like that. And well, then you Google like message bus Kubernetes, and we saw NATs, and so okay, sold. Obviously, a little bit more insight went into that, but NATs is very lightweight, and we use it to register nodes to the control plane, and also we are working on a fault management subsystem that, as the I/O errors occur within the data path, one of the things that you cannot do is determine what you should do based on that error, right? You need a holistic view of the system as a whole. So we instead of handling the error, we basically dump the error plus some metadata in the message bus, where then a cluster level service will receive that message and keeps track of how many errors and whatnot, and based on an heuristic, it will determine then to take a particular replica on or offline. That's roughly the idea, if that makes sense.
Yeah, I think so. I'm concerned that we have some pending pods. Let me check why NATS is pending. Have I given us an unhealthy cluster? I'm not nervous. You're nervous. Ready. All right, okay. Let's take a look at that node list again, the pod list again.
So it looks like Core DNS is not happy.
Yep. And the Calico Cube controller is not happy. Wonderful. That's what I get for trusting get nodes. Let's see. That doesn't look right. I'm just going to delete that pod and see if it magically fixes itself. Computer says no.
The error message is about taints and tolerations, right? Do we have to
so
dig into that?
Well, I mean, that's not what I was hoping to do. I'm going to edit the node and see. I don't know why we have an uninitialized label. I'm just going to remove it. All right.
Hey.
Yeah, I have no idea what is going on there. I should probably remove that from all of our nodes, though.
This is the OpenEBS / studying for your Kubernetes administrator exam episode.
Yeah, come and get your CKA learning how to unfuck your cluster during a demo. Like, okay, I'm just going to remove the tents. Oops, save.
Oh, just thinking about if the NVMe over Fabric kernel module is on the machines as well. I just thought about that actually, which is
okay, we can take a look at that. All right, let's. I've got at least a good few there that are running. All those pods are happy. My cluster is happy. NATS is now happy. Cool. Problem 1 resolved. Problem 2 is you're worried about the kernel module, right?
well, worried is like so.
Oh, I think you pulled his cable out. All right, well, you fix that. I will just edit the last node while I'm here. Or was it the last 2 nodes? You still there, Jeffrey? Nope. Can you hear me?
Sorry, yeah, I don't know what happened. Wireless technology. What operating system are you using?
It is a Ubuntu 2004.
Okay, so let me double check.
So if I just run an ls mod, is there a name of a module I should be looking for?
Actually, the quick start talks about it as well. So but I think it was in the prerequisites. So
the quick start will talk about it, Jeffrey. That's an oversight at this juncture.
Yeah. So
we have
there it is.
No, I
that one.
apologize.
Yeah. Sorry. Yeah.
So we're looking for NVMe-TCP and NVMe-T.
No, just the TCP one. The other one is not needed.
Okay, so I can just mod probe that, right?
Yeah. So
there we go. Easy.
easy peasy lemon squeezy. Okay. Well, that's good.
Cool. Now there's a command. If I go back to, or let's go back to the deploy one, right? So I deployed NATS, and then it wants me to just check NATS it's happy, which I'm okay with. I think it was running. And now we need to install the CSI node plugin. Which
this is the pre-flight checklist.
Hey, if all I need to do is remove some taints from nodes and copy and paste a few more commands, I mean, I think we're doing pretty well. So we got 5, so that looks good. And now control plane. I love it when the docs just work. I mean, it really just makes this a lot easier. Kudos on the docs. I mean, the only thing that's gone wrong so far is everything I've done up front.
Yeah, don't say that too often because Glenn is on the call and yeah. No, but that really helps a lot. Yeah.
Yeah, just, I mean, as someone, I mean, I'm pretty much a technology magpie. I just get to play with technology every day, new stuff, and see what happens. And when the docs work, it just makes such a difference. So I don't want to give you too much of an ego here, Glenn, but so far so good.
It's okay. I feel that you're putting me on a pedestal that I can only fall from. Fall from grace probably shortly.
Exactly. I just like to build people up so I can watch them fall. That's it. Okay, so that gave me... oh, I was just a bit too quick. Right. Is that us?
That is MSN, so it's a tribute to the old chat utility that we all grew up with. But that stands for Maya storage node, and that is one of the things that we use NATS for. So as Mayastor starts up, it starts to look for the message bus, and then through the message bus, our control plane gets the message and then creates this CRD. And when you describe the CRD, it should show you some information about the node and stuff like that. It's a namespace, I think.
Right,
So yeah, it's a little bit annoying sometimes, but yeah. Right, so there you go. So it gives us the information of the gRPC endpoint and things like that. So this is not, how to say, very useful information for a developer necessarily, but it does show you, like, all the nodes that are there and their endpoints and whatnot. So yeah.
All right, sweet. So, I mean, the next step is configure Mayastor. So just if we had like a 30-second summary of where we are right now, we have OpenEBS deployed with Mayastor and a control plane and data plane, and that's it, right? Like,
yes, you've done a lot of work, but don't have anything yet. That's
so
right.
If I were to request a PVC right now, it's just going to...
It won't work.
Yeah.
It won't work. Yeah, exactly. Yeah, so the next step is to create pools, as we say. And we have stuff in the works, actually, and that facilitates this to make it a little bit easier. And there is NDM that also makes it easier. But I think for the purpose of this exercise, I think it is probably just easy to look on the nodes, which is the disk device that I want to use, and create a thing like that.
So I think... okay. I was going to say we might get away with just using SDA on everything, but that's not the case at all.
Yeah. So you can just pick one or two nodes or whatever.
So I guess we want to use the ones with the NVMe disks, or is that am I wrong there? Does it not matter?
It depends a little bit on the NVMe drive exactly. So if you go back to the quick start guide,
yep.
Real quick. So we talk about the schemes. If you go back up a little bit here, right? So this is how we connect to the local storage, and by default we use AIO because that's common in all kernels. If it's a more modern kernel, and I think we just re-enabled it by default, we in the development branch, it uses IOU ring. If you want to go like really, really fast, there is a scheme that's not documented here because it's very difficult to use still, and that is PCIe, right? So ideally, we would tell the kernel, let the NVMe device go, we'll handle it for you. But that's rather complicated.
So that's not the one we're doing? Is that?
Well, we could, but I would not recommend. I mean, it can be a long exercise because we would need to figure out the PCIe BDF and then, yeah.
All right, so we're going to go with the NVMe over Fabric option? Is that right?
Well, I would just, if you go to the first example tab.
Oh, this one?
That one, and just, so the array of disks, we only accept one disk still. Put any disk in there you want to use, and it will just use whatever.
So I think I'm just getting confused because I just assumed from this example that I had to use something that was exposed as SD, but I could still use /dev/nvme01n01. Is that?
Yeah. A block device. Yeah, whatever. Yeah.
All right, let's start with the 2 disks with the 3.5 terabyte NVMe drive.
Sure.
Okay. So let me create this file. Let's not apply it directly to the cluster. Just so, because I'm assuming I'm going to have to modify this a little bit, right? So
you're certainly going to have to change the node name in the spec section to the node on which you're creating the pool.
Okay, so we'll call this pool1.yaml, and I need to change this to be the value from here, I believe. And was there something else you said I had to change there?
Yes,
the node
the
name.
node name, absolutely.
All right.
A
Is
pool
there a way for me to say, my cluster is made up of 3 different node types. Is there a way for me to say identify nodes with this label and expose this disk?
Not at this time.
Right.
Good suggestion. Not at this time. And indeed, as Jeffrey says, we do have something in work to automate this aspect going forward. But that's a good suggestion.
That'll be the only one I have.
Which still comes back to, no, I'm sorry, you're going to be cutting and pasting this for now.
All right, so this will be node pool 1 and node pool 2. I've got this. Does that look okay? I've not made a mistake.
That looks good.
All right,
Yep,
awesome.
that looks good.
So I can apply pool 1. Okay, so does that mean I can run get Mayastor pools?
Indeed. However, you would
Namespace, right?
need to be in the namespace indeed.
And spell it right.
And spell it right.
You can also type
thing.
MSP. It's like shorter MSP.
MSP. All right, so I have 2 storage pool online now.
Mm-hmm.
Yeah.
Am I done? Is that it? Can I go home now?
Now we need to actually create a PVC.
We'll be needing a storage class. Yep, we'll be needing
storage classes, all that stuff.
Mm-hmm.
Yeah.
Okay, so storage classes we can do. Let's just continue to add to this file. I'll make sure all of this code is... it's mostly copy and paste, but I'll still publish the code to GitLab anyway. So Mayastor...
we should change that to nvme or nvmef, however you want to phrase it. And the protocol nvmef.
That will need to be... that will need an F in it.
Yeah, it's... so the E needs to go? Yeah.
All right.
And do we want to set the replication factor? Do we want to have 2 replicas, or are we happy with 1 for testing?
Ooh. Now that you've said that, I kind of want to set it to 2.
It'd almost be shortchanged to have 1, wouldn't it?
And I could just apply this. Is there anything else YAML-wise before? No. Okay, let's just get that applied then. All right, so now I have a storage class. So now I can run some sort of database that consumes a storage class, right?
No, now you need to create the PVC.
Well, I was assuming we deploy a database with Helm and it'll do that for me. Is that what's on this next page?
Oh, yeah, well, so I'm like the, so I always do it this way because this Helm thing is too fancy for me. But if you want to run Helm, I guess that would work too. Yeah.
No, let's stick to the docs. Let's not deviate because then it's my mistake when it goes wrong, and I'm already over 2. So let's continue to add to this file. So we're going to create a PVC. We'll just call this SuperDB, and I can just pick any value, right, for the size. So it's going to use because. Let me clarify my understanding is correct here. We have exposed 2 3.5 terabyte disks to Mayastor. It's created a pool that's replicated. So I've got 7 gig of storage, but 3.5 gigs that is available. Is that correct?
No, yes. So it's well, no, yeah. It's an interesting way of thinking, though. So I can certainly see why you think that way. But the replication model is on a per replica, right? So you have 2 decoupled 3.5 terabyte pools that can store whatever, right? But when you create a PVC, you say, I want to have 2 replicas, and we will look for 2 pools on which to put the replica. And then and only then is it like we replicate that data. But the pools themselves are a thing on their own.
Yeah.
So you oh, sorry. Yeah, Kieran. Kieran can explain this better.
Yeah. So we've done this with almost all the pools, the same convention. So the storage is not aggregated from different nodes. It's kind of stays on that node. And when we talk about like a 5G volume that you create and you specify 2 replicas, it actually saves 10 GB of data. Each replica has 5 GB of data when it's full. So it's a synchronous replication of the entire data on each of the replicas.
Okay, so right now, my pool is Is a pool always one disk? What I mean is, like, if that actual disk dies at a physical level, then the replication doesn't help me at all. Is that correct?
Yeah.
So if for the PVCs that have more replicas, they will survive. For the PVCs that are on there that only have one replica, they're gone.
Okay.
But that's the idea, that the developer gets what he asks for, even though it might not necessarily always be what he wants. So we are looking into, it's like, well, maybe we want to have local redundancy, as we call it. So you create a pool, and that pool by itself is also redundant. But that comes at a cost in terms of, storage. So
there's traditional
several ways to skin a cat.
Yeah.
Oh yeah, sorry.
So traditional operations wise, then, I mean, when I'm in this kind of situation, from my experience, I would probably RAID the disks on a hardware level. Is that still something that would be recommended?
Depends. Right. So let me put it this way. Let's say that I am a developer and you're a company and I work for you, and you ask me to deploy something in Kubernetes, and I see 5 storage nodes, and I think, oh, let me make sure that I don't lose that data. I would type replica as 5. So that means that the system finds nodes suitable to put those replicas on. And then if one of the nodes dies, I have 4. Another one dies, I have 3, and so on and so on. If I say, no, in the cluster, find a pool, just put that replica on that single pool. That pool dies, I lost my data. Right?
Okay.
Now, that's not to say that we cannot make the pool redundant. We could, but I'm not sure if that traditional model, right, would be always the preferred way. So. Yeah.
Okay, that makes sense. No, that's good. Okay, so I now have a PVC. Let's go back to our... I'm not going to verify the claim. I'm pretty confident.
Famous last words.
I know. Okay. Like, let's run it. And I called it SuperDB. Okay, it worked. All right, so now... it wants me to actually check the PV itself. So, volume. All right, that looks good to me. So,
yeah, this is a CRD, and that shows you the. So we've created this almost like very small storage network in the Kubernetes cluster, and it can show you the details of how that thing is built up in terms of where are the children, as we call them. So there's an additional CRD that does that. Yeah.
Yeah, it would be cool to do a -o YAML on that one.
on the MSV.
Yep.
Oh wow. So yeah. So let me see. Let me digest this.
Oh, we got replication here.
Right. So there's the Nexus, and the Nexus has children, which maybe we should call them replicas. But anyway, and so the Nexus writes to those 2 children, and the children are replicas on pool on node 2 and pool on node 1. So whoever now mounts the PVC eventually writes to pool on node 2 and pool on node 1.
Okay.
It's like simple mirroring, effectively. Yeah.
Jeffrey, again, like, I'm asking some basic questions here. Why is one URI nvme and the other one is PDEV?
Yeah, that's a good question, Kieran. Optimization. So the Nexus itself figured out that, hey, wait a minute, one of those 2 replicas is actually on the machine that I'm sitting on. It doesn't make sense to do that over the TCP socket, right? So I'll just, mem copy it. Well, it's actually serial copy, but, we bypass the network there. And future optimizations, we want to give it an affinity such that reads always go from the local one, things like that. Oh, right in time, and bless you.
Thank you. Yeah, so let me I want to make sure I've got this right in my head. So we've created a Mayastor volume, and it is available on both of those nodes. So my workload has the freedom to migrate between either of those two nodes if it wants that PVC. Is that correct?
No.
No.
Close. So I think next time around probably should have a picture. So the Nexus is a nvme over Fabric target, and any node in the cluster can connect to the Nexus over nvme over Fabric. Also iSCSI, but we're not going into that. But that's how a node would connect to this PVC. And then the Nexus then doesn't do anything other than, so it's stateless. There you go. But it needs to get this IO out somewhere, and it pushes those IOs out to the children or replicas, as it is also written down here. So the Nexus receives the IO from your workload and pushes that out to those two nodes you see there, pool node 1 and pool node 2. That's how it's like a RAID mirror thing, right? Mirror.
Okay.
Very
So
simple.
if I deploy a pod that consumes this PVC, it's going to be scheduled on one node and always that node there forward. Is that right?
So the workload itself can go anywhere, because the way that you connect to the Nexus is over a Fabric, right? That's networked. But likely the scheduler will put it on the same node, because I think we have some rule affinities in there that prefer it to go that way or that way. But you can. That's what I meant with. That's the reason why we have the message bus, right? You don't want to have the Mayastor service run on every node, right? So let's say you have 5 nodes, only 2 of them run Mayastor, and you mirror them, and the other 3 nodes just connect to the Mayastor instances, right?
Okay. We have a question in chat, which will pop up now.
Oh boy.
So does the Nexus pick the I/O from the app itself, or how does that work?
Pick the I/O from the app itself. Not sure.
I was hoping it made sense to you. If you could give us a little bit more detail in the chat, we'll try and come back to that question.
I think, Jeffrey, it's a question about, does it use POSIX? Does it mount? Or can the app directly communicate to the Nexus?
Oh, right. Good question. So we can actually do, well, maybe I should stop confusing people, but we can actually do both. So if you write an application, you can use an API to directly write to the Nexus without anything else, right? But the way that is set up now is that the node that is going to connect to the Nexus will use the nvme over Fabric TCP module that we loaded in the beginning, right, to connect to the Nexus. So if you're familiar with iSCSI, just replace iSCSI for nvme over Fabric. That's it.
Okay, so I think there was something really cool there. Like, so what you were saying was, so my application doesn't have to change. I can write to a disk, and then the magic happens for me. But I think what also you alluded to there is I could make my application OpenEBS or Mayastor aware and write directly to the Nexus.
Exactly. Yeah, and in fact, we've done a lot more work there. And don't get me started, but we Jan, who was on the call, has actually written a VirtIO driver that allows you. And we actually did this for Go. You have these what's it called, interfaces, right? Read at, write at, that type of stuff. And if you implement the interface, you can, use it the way it was like a file. And so you could use Go reader and writer to write to a VirtIO device that would immediately write into. It wasn't called Mayastor back then, I must say, but so yes, that is possible. And I think that that's in fact the real future, because why would you go through the operating system anyway? It's like, yeah, because you have a file system. Well, file systems, why is there a file system still? They used to be there because the caching and but it's like, do we really need to? That's what they mean with DAX file systems, DAX, direct access file system. It bypasses the page cache. It's like, sorry, kernel, you're just slowing us down.
All right, cool. That's exciting. Definitely something for another session, I think. Okay, I don't want to keep us too far beyond what we actually had scheduled. So let's assume that in the next 12 minutes, we want to show off everything that we've done so far. Are we going to continue with the docs, or is there something we should jump straight to?
So the if you deploy a FIO pod, then it would just mount that PVC and run FIO against it with some very odd defaults, like very small. But yeah, you could run that, and then it would, show you some output in terms of.
Do you want to modify that, or do you want me just to apply it straight up?
No, I think it's fine for the sake of the stream.
I think we changed the name of the claim, though, didn't we, Jeffrey?
Oh yeah, shoot.
The FIO YAML is expecting it to be called MS Volume Claim, and I think we went to SuperDB, did we not?
Sorry.
No worries. Don't worry.
So if I run get deployment, I'm assuming that's just created a deployment here. No.
I know it's just a flat pod.
It's on the
default.
Yeah.
Yeah. Okay. I can't modify that. Okay, so I'm gonna have to delete the pod, and then I will need to pull this down.
That was a CKA question. Why can't you modify a pod?
Can't you modify a pod? Why not?
The spec's immutable.
Yeah.
Oh, why?
Because you're not supposed to work directly with pods. You're supposed to use an abstraction.
Oh.
So this is awesome. I love that you're using nexary.dev.
All right, isn't it amazing?
I'm a huge fan of Nexary. It's so cool. If you're not familiar with it, it's like a dynamic Docker registry where you just tell it whatever commands you want. Like I could just add wget /wget to this. And it adds it in the image. So good.
And it's always freshly compiled. And if they commit a new version, it's Anyway, yep.
All right, so change that to SuperDB. This runs tiny and sleep.
Yeah, and so then what we typically do is we exec into the container, and then in the container run FIO because you want to see output, right? So.
All right, so we deploy FIO. We should see that exists this time. Yep, curating, that's better. I'll just run a watch on that. There we go. Good. I thought I was going to have to think of a joke there. So, and we want to exec in. I'm in. So let's see. Oh yeah. This way.
Yeah.
That's all right. I just copied this. So, can someone tell me what FIO is?
A flexible I/O tester. It's written by Jens Axbo or Axbo. I'm not sure if I pronounced his name correct. He's a guy from Denmark who works at Facebook, and he is the kernel maintainer of the Linux block layer. So everything block device related, he's kind of like responsible for, if you will. And in order to test the stuff, he thought, I need a tool, and there you go, FIO. So it's like the de facto standard to test block devices, file systems, whatever. Yeah. It has a lot of options, and so
you can basically simulate any kind of workload with this: sequential, random, small size, big size, overwrite. That's a cool part about it. So, for example, like one of the things that we did is Postgres. You kind of can replay that and then convert into a FIO test file and then replay that. Very flexible tool. Flexible IO is also on the other. Right?
All right, it's doing its thing.
Yeah, it's only
about 1 minute.
Yeah, I think the runtime is set to 1 minute. Yeah, but the what does I want to say? Yeah, it only creates a small file, obviously. So an interesting thing to know is SSDs have a certain span. Or at least I'm not sure what the nomenclature is, but a big CPU vendor calls it spans. Let's call it that. And if you look at an NVMe SSD, it has several chips, right? And what you want to do is when you run a workload, you want to touch all the chips because that's how you get the concurrency, right? If you write to all chips at the same time. And one issue with SSDs is like, so if you have a small data set, you're only touching a subset of the chips, and therefore you don't have optimal performance, right? if that makes sense. So you're not touching all the chips at the same time. So there's some of that thing to consider when running with these things. But long story short, that's it.
Excellent. So,
At a scale of 1 to 10, how difficult do you think this was? Apart from dealing with me, obviously.
this was painless. I mean, I'm pleasantly surprised. I always just think storage is going to be one of those things that you just bang your head off of it. But I mean, even, I know you said earlier that this is very much in development, maybe not quite production yet, but people can start to use it. I didn't expect us to be able to run through the documentation and just get it to work. Again, the only mistakes or problems we had were me. So, I mean,
well, yeah, it's not trivial for sure. And Kubernetes by itself is also something that is non-trivial, even though it makes things easier to deploy once you get a hang of it. It's not trivial, right? So, yeah, and so you can run some stuff on it and play with it and whatnot. And we haven't touched upon several other things, like, for example, it's like I still need to blog about it, but we've done some benchmarks where we pushed well over or close to 1 million IOPS on nvme devices. And for examples like, how do you define how many cores you want to use, and how do I tell the operating system to not schedule any workloads on the cores that I run Mayastor on? Because, for example, if you type ls, you don't want the kernel to interrupt the Mayastor process, where the kernel said, hey, Mayastor, stop, ls gets the run, and then, so you want to have these context switches. You want to avoid that from happening, and there are various ways to do that, but the canonical way is to boot the system with certain arguments that isolate CPUs and all stuff like that. So if you really want to push the system, there is more work to do, to be fair. So this is like the happy path. Everything's hunky-dory, but if you want to get to the optimal performance, there's a little bit more work.
You can squeeze the Juicero packet with your hand and get some of the juice out, but there's a special machine you can put the packet in and really get all the juice out if you want.
Yeah.
It sounds like there's a lot of tweaks and things you can do to get even more. I think
that's what makes me so excited about it, because I work for Equinix Metal. I have all of the bare metal compute that I need access to ever in the world, and now I get to run
don't make me jealous. I don't think that's appropriate.
And now I have a storage layer that is built with really cool technology like Rust and doing really cool things, and I can squeeze the performance out of it to millions, or 1 million IOPS. I mean, I think that's just terribly exciting, and
yeah. To tie this back to kind of sorry to interject, the original presentation that Kieran introduced with, to get started, the most important thing is to have it just work, to have it install and just be there and up and running. And over time, as applications grow, as your business or your project grows, that scale tends to favor customization, I like to say. So there's a lot of more knobs and a lot more buttons you want to turn and press. And our solutions, OpenEBS and Mayastor, are kind of built with that in mind. We want it to be easy to set up and get going, but we also want to give you those knobs and buttons for when you're ready to scale and do that extra stuff. Awesome. To really get going.
Well, so before we wrap this up, is there anything anyone here wants to show before we conclude today's session? Is there anything that we haven't covered that we think is important to?
I'm thinking, well, I mean, we could go through some logs and see some stuff on how it, but I think this is pretty much it. We tried to keep it very, very simple at the beginning, and then get the foundation right, and then start to come up with some more sophisticated stuff. Yeah.
Awesome. I think this was a great introduction, and we got hands-on, and we showed how it works. I mean, I'm definitely going to speak to you all afterwards and see if we can line up another session where we dive into all those other concerns OpenEBS tries to bring, snapshots and backups, and really try and understand the full landscape of storage on Kubernetes. But I think for today, this was fantastic. And I just want to say thank you to all of you for joining me. like I said, that's the first time I've had this many people on the stream, and it was an absolute pleasure. So thank you.
Well, thank you.
Thanks for having us. Thanks.
All right. Well, you all, you all have a great day, and I will speak to you all soon. Thank you.
Bye-bye. Thank you.